Hi everybody. So this is my first video in the series on an introduction to the normal distribution. And this distribution of a set of data involves most of the data values falling somewhere in the middle and only a small proportion taking much higher or lower values. So you can see in this histogram that most of the data points fall between the 1.6 and the 1.9. The modal class is between 1.7 and 1.8. But as we move away from this, the number of data points drops significantly, and this is true on both sides. And when we get a distribution like this, where we have a smooth symmetrical peak, often known as a bell curve, we can model it as a normal distribution. And you'll notice that the x-axis is a continuous scale. And examples of continuous variables that can follow a normal distribution include height, weight, mass, and time. So when a set of data is distributed normally, we have the normal probability density function. And the area under the curve can be used to calculate the probabilities of an event that is normally distributed, where in a normal distribution, the mean is equal, the median is equal to the mode, the distribution is symmetrical, and there are points of inflection, one standard deviation from a mean. You can see here, and a point of inflection is where the curve changes from concave to convex. So at this point and at this point, you can see here the curve is concave, and then as we move in this direction, the curve becomes convex. So if we look more about the area underneath this curve, we define mu as the mean average and sigma as the standard deviation. So 68% of a total area lies within plus or minus one standard deviation of a mean. So you can see this would be the average, take away one standard deviation at an area of 34. And the same is true on the other side, where you've got the average plus one standard deviation. And because it is symmetrical, 95% of the total data lies within plus or minus two standard deviations of a mean. That would be from here to here. And 99.7% of the total data lies within plus or minus three standard deviations from the mean. Now, we approximate this 99.7 to 100, so our percentages work out quite nicely. So when we describe a normal distribution, if a continuous random variable x is normally distributed with a mean of mu and a variance of sigma squared, then it is written as x, the random variable, is distributed normally with a mean of mu and a variance of sigma squared. Okay? So if we look at when we can apply this model, explain whether each of these variables follows a normal distribution model. The distribution of waiting times at a bus stop as shown below. Where you can see this distribution is not symmetrical. So because of this, you would not use a normal distribution model. For part B, with shoe sizes of 200 randomly selected men at a shoe store. While shoe sizes is a discrete measurement, you would have size 6, 6.5, or 7, but you wouldn't have a shoe size of 6.01, for instance. So because it is discrete and not continuous, you would not use a normal distribution model. For part C, the raw scores of 50 students in a test out of 80. Again, the raw scores would be discrete. You wouldn't have a score of 50.06, would you? So again, the normal distribution model would not be appropriate. Then for part D, for masses of mice in a random sample of 100. Well, this could be modelled normally. What we would do is plot the distribution, and if we had a smooth curve, which is symmetrical about the mean, then yes, that would have a normal distribution, okay? Because we know that our mass is a continuous variable. In the next video, we're going to look at calculating probabilities using a normal distribution model.